Hello everyone. So this is my first long format video on YouTube, and here I will dive deep into the spacecraft engineering for the project Hail Mary. So the primary target is to look into that how accurately the spacecraft is designed with all the mystical elements and how beautifully the engineering is done in the spacecraft. So that's the main point that we will hold in this YouTube video. And there is almost no spoiler in the story because I haven't seen the movie yet, and I have not really read the book as well. So yeah, but we will dive deep into the very systematic discussion about all the engineering elements and the major concepts that you might feel interesting or might be very helpful when you watch the movie. So that's the whole goal of this video. So giving you some context, so firstly I have a script in front of me, and I'm also not a native speaker of English. So I might stop a bit, might lost in somewhere, and search some words that's very useful. But yeah, let's start with the thing. So before we dive deep into the engineering stuff, let's give you some context of this. So the story begins somewhere where the sun is dimming due to a mystical element called astrophage. So let's assume that astrophage is a microorganism kind of element which is consuming the sun, which is taking away all its energy in the near future, and it is also spreading throughout the solar system. And I think like Earth only 30 years to live when the astrophage completely destroys Earth. So that is where the main story starts. Now, to overcome this situation, the NASA astronauts, I don't astronaut or not, but anyway, the main planetary protection group of the Earth decides to go to a Tau Ceti system, which is about 12 light years away from Earth. And they choose the Tau Ceti system because Tau Ceti have shown that there are some solutions to tackle with this mystical element called astrophage, and they want that someone should go to Tau Ceti the planet, or how the problem of astrophage getting mitigated. So yeah, that's the only way they found for some reason. But yeah, like that's the story where Ryan Gosling in the movie gets to go to a mission to Tau Ceti, and they do some stuff there, and in the meanwhile they meet up Rocky. But yeah, we are not discussing that part, but yeah, that's the whole goal of a mission. So this is the one way multi-year deep interstellar single crew mission that it is that is the mission profile for this particular mission. And interestingly, they are using the astrophage itself as a fuel to go to Tau Ceti, which is where the main engineering starts. When so we know the mission profile, where it is going, and we also know the fuels so far that we are using astrophage as a fuel. So we will dive deep into the how astrophage as a fuel is contributing to the emission. But before that, I just mentioned that the city system is about 12 light years away. So how far is a light year? Like most of us who are not from the STEM background have almost no idea about what a light year is. And also, if you have an idea, don't know how big it is. So it is very important to realize how big is a light year. So light year is the distance that is used in the astronomical as a astronomical unit. Where people study astronomy, they use light years quite often to measure the distance between one star to the another. So light year is calculated based on the speed of light, which is the constant. We have the constant of speed of light and how much a light can travel in 1 year. So as you can imagine, you must have heard of the fact that it takes about 8 minutes for the sun's the sunlight to come from the sun to the earth is about 8 minutes. So you know how those are calculated is because of the light here. So goes travels in the 1 second, and we multiply it by how much it travels by 1 year. So simply, so how much the light speed of light is about 300,000 kilometer per second, and when you see it that how much it is traveling in 1 year, so it becomes like 9.46 trillion kilometers, like massive, massive, massive. So let's just put things in perspective. So the sun to earth in terms of light years is just about 0.000015 year light years. Um, if you imagine in our solar system scale, it is about the solar system diameters is about 1.5 to 3 light years. And you must have heard the all the space geeks have heard about it. There is a star called Proxima Centauri, which is the nearest star to our Earth, and it is about 4.246 light years away from Earth. And the Milky Way galaxy, where our solar system is situated in this whole universe, is about 100,000 to 120,000 light years in diameter. So in perspective, you understand that tau set is just 12 light years away. So it is essentially in, I assume that it is inside the Milky Way galaxy. And so yeah, like it's massive, far distance, but it's inside the Milky Way galaxy. So yeah, I think that's fine. That's good story. So how can you travel about 1 light year? Like, is it have anybody traveled? I think yeah. Like, I think the Voyager spacecraft traveled 1 light year. I don't like it's above, like it's outside the solar system right now. The Voyager missions and the spacecraft. So I assume it must be 1 light year at least. I don't know. But if you look into our Apollo spacecraft, which is the spacecraft that took humans to the moon about 50 years ago, if we use that traditional rocket to travel 1 light year, it takes about 27,000 years. So the fastest, maybe the fastest rocket that we use takes it will take 27,000 years to travel 1 light year. So yeah, like it's super crazy. Moving on, we will just dive deep into that. What does this astrophage as a rocket fuel does mean? So astrophage by definition is a mystical element which transforms the matter to energy directly. And so you must like yeah, you should have by far heard of the equation called E equal to mc square, which is proposed by Einstein. And like it just equates the energy to the matter. So mass and energy is convertible as per the equation, and if you apply that equation, you can see that if a element that is transforms like a matter to energy is like how much energy is this. So the energy which will be produced is that matter that is let's say for example it's 1 kilogram times the c square, which is the speed of light square. And if you do that mathematics, it comes out to be that 1 kilogram of astrophage can generate 90 petajoules of energy. Like that's crazy, like out of this world. So the best so the whatever the best rocket engine which we have in earth is that the liquid and oxygen, we mix the liquid and oxygen, we burn burn that oxygen to generate the propulsion system for our for the rockets. And if you look into that, it is about like 1 kilogram of that mixture can release about 13 megajoules. So megajoules of energy, the comparison to the astrophage. So astrophage is about 7 billion times more energy. It's crazy, crazy, crazy. Like how much crazy in terms of, let's say, as if you can take a reference of the atom bomb that was dropped in Hiroshima, it generated about 0.063 petajoules. So like 90 petajoules and 0.063, like it's unimaginable amount of amount of energy that's being released by Astrophage. But yeah, it's good because it will help us to go to other planet and save Earth in the meantime. So that's really great. So look into that, we saw in the movie that there are only 12 years of left for Earth, and there are only like they need like 12 years, light years needs to be traveled in the 4 years period. So like, so if that happens, like as a astrophage, as a mission, like as a fuel, and you have to travel 12 light years in 4 years, so that's quite crazy. And we are also using the concept arts that we got from the trailer, and some of the snapshots from the like the release when the Project Hail Mary was released, some of the snapshots from there. So we get the concept art from that, and we found that okay, there are three engines. And in the, so why are there three engines? So in the aerospace engineering terms, it's called like the three cylinder engine cluster. And it's like why, like there are two main purpose. One is redundancy, because that one of the, if one of the engine fails, there are other two engines that can take the lead and go to and complete the mission. And also, like when you have three engines, you can fire one slightly more or slightly less to steer the engine towards any other direction. So you don't need any external thrusters to navigate the ship. Like if you have one engine, you don't really know how, like you have to have external thrusters to navigate the thing. But now when you have three, you can just navigate with those like like if you change the propulsion a bit, you can navigate the ship's direction. So that's the main purpose of having three engine. Like similarly, if you see that our lot of our recent engineering developments that's being done, like the SpaceX Falcon 9 rocket, they have like about 9 Merlin engines in the bottom of the rocket. And if you look into the Saturn 5 rocket, there are about 5 F1 engines there. So yeah, it's just does a similar thing. Yeah, it exists, that this technology exists. So that's a good thing to look into. So now looking into that, main problem is that first question is that a human is traveling in the whole deep interstellar space, and it's very challenging because like on Earth there is hardly anyone who have who have traveled beyond, like there is no one who have traveled beyond moon. And there are very short duration missions to the moon, whatever happened. So as a human, we don't know that what really goes wrong in a very long duration, when you're very like we're spending like a 3 4 5 years in space. So but we have some data which says that okay, like in from the short duration we can predict that what can go wrong in the long duration mission. So firstly, like, so here in this story, there is a very beautiful thing. See, what happens is that when you go to space, you feel microgravity. Mm, Microgravity means like there is no gravity. You don't have the luxury of the earth pulling you downward. So everything in your body just scrambles up. But yeah, like if you just noob and don't really want to dive deep into that, so in microgravity there like you lose your bone, you lose your muscles, and ultimately you die. That's the plain answer about microgravity. So astronauts does a lot of exercise, and they wear special suits to overcome that. And they still it affects their health, but like it overcomes it for a long duration. So see, now to have a like a 4 year journey to some space, you need gravity. Like without gravity, your body is going to die. That's the whole thing. Now if to how can you generate gravity. So there was a, in a old days when NASA was planning to send humans to the low Earth orbit, they had a plan for a spinning spacecraft, like a spinning space station, where the entire habitat is rotating on a single point with some force, and that spinning effect actually creates centrifugal force, and that centrifugal force like helps the human to get the gravity, which is like that space station is also called the Stanford Torus, which is also a very famous concept. And that spacecraft, that space station generated gravity, and which helped the human to maintain their body mass and don't really die in microgravity. So yeah, that was a proposal, but eventually it got cancelled because it is super difficult to build. It is like it requires a lots and lots of funding, like more than what the International Space Station is. And yeah, the technological capability was not there that time. I think like there is like when they were discussing, it is about 40 years back, almost 30 years at least. So now the technology have changed a lot, we know a lot of technology, the materials have evolved a lot. So yeah, like it's possible now, like in the near future, in the next 10 years we can probably see a spinning space station. But yeah, it was not possible back then. So now what's happening in this story, so this rocket don't really looks like it have a spinning component to stabilize the body or counter the microgravity. So what's happening here in this story, the rocket that is designed is actually pushing the spacecraft in about 1.5 g, where g is the acceleration due to gravity we all feel on earth, is the acceleration due to gravity we all feel on the earth is about 9.8 meter per second square. So that's the acceleration that any object, if you just drop a thing from the top to on the earth, it just accelerates at 9.8 meter per second square, which we are calling g. Now that g is actually like keeping our body to the earth, it is attracting, uh, the gravity is attracting, as you all know. So yeah, like, but what's happening in this spacecraft is it is actually pushing the, when it is a microgravity, when there is no gravity, the spacecraft is pushing the body or the entire habitat, or let's say the space station, at 1.5 g 1.5 g acceleration throughout the journey. So that is what happening. So um, so how it is working out is actually, when you are, let's say you are on standing on the earth, so what's happening is that the earth is giving, like providing some kind of gravity, like the force it is acting, it's pulling you downward, but the ground is giving you a counter reactive force to stand there in a stable position. That's like the Newton's third law. Here also the third law applies. So what's happening is that you are just, the spacecraft is going in the 1.5 g, it's pushing the human or the entire habitat at 1.5 g per hour. So as a counter, what's happening is that it is just so you the if the human is standing here, uh, and then it is just like it is getting pushed in the other side due to Newton's third law at 1.5 g. So yeah, so that is how it is, it is working, the space station is working or providing a gravity. Now the most interesting question that might pop up is that why 1.5 g or not 1 point, like just 1 g, because 1 g is the ideal case scenario. So the thing is that if you calculate the distance, the 12 light years from the which will covered by the 1.5 g acceleration, so it will take 4 years to cover that. But instead it just takes 5.5 years, like if you use the 1g it takes about 5.5 years. So it don't really fulfills the mission. Now you might think that okay, so there are about a lot of time is left on earth, it is about I think 30 years is left on earth to just go there, so why hurry and don't do. So the distance, though, the time that is being taken by the spacecraft to travel to the next the tau city is 4 years, but from the Earth's perspective it is about 13 to 14 years. So it will just not work, because you need to also send the information back, so it will take that time. So 5.5 years is not possible. We will discuss the time dilation in the next bit, when we'll discuss the journey and we'll calculate the things about the spacecraft architecture in a bit. So, and also like the 1.5G also acts as the high compressive, since so the Grace, the hero of the movie, is actually traveling in hibernate conditions throughout the journey, and it is not really doing any activity. So even it just feels like he will just feel some heavy weight on him when it is like 5G. So if he is a 70-kilo man, so he will be bearing a load of 105 kgs. And since he is hibernating, it have a very little impact, and he's and yeah, like he is having a good position in that. And it's a story, just believe it, it's a story, it's a story. Yeah. So now moving on to the main bit, where so it the calculation, I have not really the super idea, but yeah, whatever basic idea I got, I also took help of Claude to help me with go through this idea a bit. So the distance to Tau Ceti is about 12 light years. So the ship's acceleration is 1.5 g. Time to travel is about 4 years. So now what's happening is that if you are, so the target goal is that it is starting at zero velocity, and it is reaching the Tau Ceti at zero velocity, because you need to decelerate when it reaches there, right? So what happens is that it reaches its maximum speed in the first place, and then it just decelerates rest of the journey. So 2 years it accelerates, then 2 years it decelerates. So what's the maximum velocity that is taken by the so what's the maximum velocity when it reaches 2 years? So we know the acceleration is 1.5 g, and if you multiply it by the 2 years, so the maximum velocity becomes is like it's about 1.5 into 9.81 into 2 years, and like in seconds, and you will get the maximum speed to be 3.1 c. 3.1 c is the speed of light, so three times, almost three times the speed of light. Now yeah, comment me down that what is the law that is being broken here. Like, we know that nobody can really travel faster than light, it's not possible. But it's actually, it's true. Now there is a concept. So what happens is that, let's say, so whenever such things happen, things kind of shatter, because the space-time compression, a lot of other concepts, that the relativity concepts comes into play. So what's happening actually is, let's say somebody is on earth and it sees somebody is going in a speed of 0. Let's say 0.9 times of c speed in some place. So it have not reached, but the man here, the human on the earth, can see that it's going in the in near the speed of light. Now that man who is traveling at the speed of light now fires a bullet which is about about the speed of light, not really crossing the speed of light. So what's happening is that from this man's perspective also, that bullet is also traveling at near the speed of light with respect to him, the who is also traveling near the speed of light. So when the human who is watching, as per the Newtonian laws, it should be just that, okay, the human who have fired and the speed of the bullet would get addition, which will be more than the speed of light with respect to the human who is standing on the earth. uh, but it don't happens that way, because like the human cannot observe, or like would not observe anything that is going beyond the speed of light. So what happens is that there is a concept called relativistic addition of velocity in the, which is a chapter in the special relativity. So it just says that the speed will go close to the speed of light, but it will not ever touch or cross the speed of light. So yeah, so there is a formula for that, that is like beta equals u by root over 1 plus u square by c square. If you apply that formula in here, you will see that the velocity at which the project Hail Mary would be traveling traveling as per the person on the earth is not 3.1 c, but it is about 0.951 c, which is less than the speed of light. And so you imagine like that thing is traveling like 12 light years. And then it's just like the speed is not enough as per the like the people on the earth. So the time dilation also plays a broad role. So from the Grace perspective or the hero's perspective, he took about 2 years to travel there. But as per the people on the earth, it is like beta times the time of ships. Gamma, I guess, gamma, yeah. So gamma is the Lorentz force. Lorentz force equals 1 by root over 1 minus beta square. If you calculate that, it becomes the time on earth to travel 2 years. 2 years from Grace perspective becomes the a time of like 3.23, which is the value you get, and then times 2, which is about 6.5 years. So 6.5 years is being taken from the earth perspective, but the from the Grace perspective is just 2 years due to time dilation. So when the Grace reaches so the interesting factor is that when the Grace reaches have reached his age 4 years, when he is now in Tau Ceti, the Earth people have actually aged like 6.5 times 2, that is 13 years. So that's very interesting. You know, Grace got. I should also take the same apply to reduce my age a bit. Okay, now moving on. So we know that so let's say we put the rocket equation in terms of relativistic formula. So our goal is to look into that how much fuel is needed, and fuel is needed to calculate the dimension of this entire spacecraft. And then so if you put the formula of the rocket equation, the fuel plus dry mass, fuel and the dry mass by the dry mass, which is equals root over 1 plus beta by 1 minus beta, where beta is the peak velocity, you will end up with the mass ratio of 39.8, or like 40 times. So if you put in a simpler terms, it is like the ship is 40 times heavier when it started than what is ended, where it's ended. But here now the author in the story says that the mass ratio is about 21, which is likely due to the fact that he considered the fuel till acceleration and he didn't consider till deceleration. So and it is also like not my word that the author didn't consider the whole thing. It is as per a post in crawl space, and they did a total analysis. I know that there are people who is just crazy about this thing, but yeah, I'm also like crazy. I just dive deep into it, and you are also crazy because you are just diving deep with me. Like I don't know like who is going to apply, but yeah, it's very interesting. Like oh man, this is super interesting. So now leave that space. So yeah, anyway, it's okay. Like let's say the mass ratio is 21 for now, since like we have to have a author as a path correction. Anyway, so the fuel needed is like the initial mass into r times final mass. Like so let's say the dry mass, which is the final, like after leaving all its fuel, the dry mass of the rocket engine is about 100 tons. So the fuel mass is about 2000 tons by the Andy Weirs. But our calculation, it would be like 3880 tons when with the fuel. So with the fuel, the rocket weighs like 3990 tons. So the fuel mass is about 3900 tons. And then when you look into, let's say, we don't know the mystical density of the mystical element of the astrophage. Let's assume that it is about the density of water, which becomes that 100,000 kilograms per meter cube. And then the volume, you will end up calculating the volume is about 2000 meter cube, and the volume of each tanker becomes 667 meter cube. Now if you estimate the cylinder's radius to be 4.5 meters from the concept arts, then the height becomes 10.5 meters per cylinder. So the cylinder is about 3 story tall, and the diameter is about 9 meters. So yeah, crazy massive engine. And yeah, it's quite feasible. Like, we have these engines now. So the movie, when you look in the to the photographs of the movie, the it have different sizes. So the either the astrophage have a lower density than of water, or the tank itself can have other structural elements or the more dry mass. What I mean by that, so if you consider the astrophage density as 100 kilograms per meter cube, which is about some gas, then the tank size becomes, if we consider the tank size as 9 meters in diameter, it is about 100 meters tall or a 30-story building height. So yeah, it becomes a crazy, like a massive rocket when you consider astrophage as a gas. So now, yeah, we know that what's possible, what's going on, and what's the dimension. We have finally come to the end of the chapter. So we spent significant time understanding the dimension of the fuel tanks, and at least we got some scale about it, what's the concept that goes behind. What we saw is a massive combination of mystical biology, the astrophage, and how the physics and engineering comes together to create something so accurate for a movie. And we also discussed a lot of physics that is involved in the Hail Mary. We are planning to do some more contents on about the architecture of the Hail Mary, that how it's the spaces are organized, and more about architecture, not just physics, in the next places. Please like, share, subscribe, and just let me know that where I missed. There must be many things which I missed. And like, the spacecraft engineering is massive. Like, 30 minutes is nothing to understand things in depth. But yeah, like, if I missed anything or if I have said anything wrong, just let me know in the comments. And yeah, definitely let me know what you enjoyed the most. And if you gave me a good response, then I can really make videos on more of spacecraft engineering, like maybe some spacecraft from the Marvels universe, something from the Star Wars, Star Trek, or something like that. Or if you have any, like, if you know any people who are explaining these shitty things in the world, then also let me know. I'm very interested in these things. So yeah, see you. Yeah, also I to Instagram page called the Laser Lab, where I post some shots on the human space medicine and also space architecture. Those are my field which I do PhD in. And yeah, next time. Bye bye. Thank you.